Good afternoon, everyone. Uh, Welcome to our seminar, which is on embankments of soils. And we're going to talk about lessons learned in the last 50 years since I started working on this subject. My name is Alberto Ortigo. I I have a PhD from the I hold a PhD from the Federal University of Rio de Janeiro, nearly 45 years ago. And in the last couple of years, I became a fellow of the ICE, Institute of Civil Engineers, a charter engineer in UK, and a PE in America, uh, in North Carolina and South Carolina as well. And what are we going to talk about? Hmm. Okay, this is an overview. Uh, that's what the main theme, lesson learned after after a 50-year experience. I'm going to address common problems in embankments or soft clay. I'm going to address the main aspects of site investigation and how I learned through mainly through dry embankments, which I'm going to describe, and I'm going to talk about ground improvement solutions that have not worked well. I'm going to talk a little bit about instrumentation monitoring, not too much. And in the end, we are going to discuss the philosophy of how to deal with soft soils. So, welcome. Let's get started. Uh, Common problems that I have seen along my life. Failures like that due to bearing failures on soft soils. I've seen this one. It's a road in South America. This is another bearing failure which I had the opportunity to see. It took place in northern Brazil due to bearing failure. As a matter of fact, the I have when this construction started, I have suggested a solution for that, and they decided not to do, which was to reinforce with the geosynthetics. I have seen many failures in, on of embankment soft soils, like this one, you know, and this is probably the largest one I have seen. It was a very high embankment, and we see here. Let me get the pointer. We see here the cracks, you see, uh, and the bulging of the clay in front of the embankment. The other thing I've seen too many times are settlements on approach embankments. And this leads to big problems because there's a bump. I've seen these on railway projects and highway projects as well. And on railway projects is a big problem because the train bumps, and this may lead to mechanical problems, mechanical failures, which have to be addressed. And ground settlements around building. This is a project that I worked. I was very young in 1978. I worked in a company in Rio de Janeiro, and they asked me to carry out some pilot testing. That's all I did in 1978. And then in 2006, I was invited to come to the site because of the problems. And ground settlements around buildings. I was not involved in the project, just on the pilot testing, but the fact they did not carry out ground improvement led to lots of problems afterwards. Well, let's discuss a little bit of site investigation for uh, soft soils. And these here are the most important types of site investigation. The SPT, which has some usefulness in soft soil, but not very much. What's essential is the CPT, which we are going to discuss. The other essential is the VST, and DMT can be helpful. Pressure meter, this is usually I don't like very much for very soft soils. I use pressure meter for harder soils, okay, but this is going to be another discussion. And I have published these two books in the past. I was an academic for 25 years, and in that time, I published the first book on soil mechanics in the light of critical state theories, very much devoted to soft clays, and then the other one, which is the Handbook of Slope Stabilization, uh, has nothing to do with soft clays. But anyone interested, just drop me an email or WhatsApp, and I'll be very pleased to send you copies of these two books. Okay. Well, in situ tests, we have different kinds of two main different kinds of in situ tests. One of them is about to do profiling, and it brings it analyzes stratigraphy, and parameters are obtained through correlations. These these tests, usually CPT and mainly CPT and also SPT, they provide parameters obtained through correlations. And we have the calibration tests. What's the difference between profiling and calibration? Calibration tests are those in which stresses and deformations are known, and parameters are obtained through numerical analysis. Let's get into that. What are the most important profiling tests that we do? SPT and CPTU, almost all jobs in soft soil will have those. Also VST, the Vinci test, which I'm going to talk. Also, we can have the maquette dilatometer, but although it can be useful, we're not going to discuss this because this would take much longer time. And the analysis usually we do through empirical correlations, okay? And then we have the calibration tests, which are they? The main one is the back analysis of trough embankments. I'm going to address this with several examples. We can do the pressure meter. Usually I don't use pressure meter for soft soils. I use pressure meter for harder soils. Self-boring pressure meter could be a very interesting tool, but it's very difficult to carry out the test. Usually we need a PhD or someone with lots of experience to do the test and to analyze the results. Menar pressure meter, a very interesting tool, but I use it for harder soils, usually those in which I can't use the CPT or the VST. Plate loading tests, usually mainly uh, for pavements, and horizontal plate loading tests, which are usually replaced by a Menar pressure meter. In order to go on, we need to understand a little bit about variability of soil properties. And this came up by many years ago. I attended a talk by Fred Kuhawi in which he addressed this, and I got the speakers from his work. And what we see here is that the main test that we use uh, for soft soil, which is the CPT, it has the minimal coefficient variation. So the repeatability of the test is very good. And why? Because it doesn't rely on the operator. The other tests like SPT very much rely on the energy which is transferred to the soil, and then the variability could be very large. This mechanical CPT, which no one uses anymore, vein testing also, there's a lot of interference of the equipment, and we're going to discuss that later on. DMT is a very good test, but a little more expensive, at least twice as expensive as the CPT. So I use it. It's very good, but today I would prefer CPT more than the DMT. Pressure meter, as I've told you before, I use for hard soils. It's much more dependent on the operator, dependent on how the borehole, the quality of the drilling, etc. Self-boring pressure meter is, I have done some long ago, but very, very difficult to carry out and to analyze the results. And here's an idea of the variability of soil properties, okay? So As we see here, those which are very important for soft soils are those which have the enormous variability. The undrained strength of a clay can have enormous variability, and the coefficient of compression to calculate settlements also presents a very a very high variability because mainly the coefficient of compression is related to sample disturbance. And I'm going to show you how to use CPT in order to get reliable uh, settlement predictions and not to use too much laboratory tests. Of course, these tests are very important to characterize the soil, and the variability is just given here. Okay. Well, let's go to first kind of test that we used was the SPT. This is a very old picture from probably the 50s. Uh, People carrying out SPTs with a tripod, and the test is very simple, in which we drive uh, 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 a sampler, a standard sampler, into the ground, and we count the number of blows in order to make the sampler to penetrate 45 centimeters. These are very standard tests. I'm not going to describe with lots of details. But drilling sampling is always absolutely necessary. And usually, if we have a profile like that, in which we have uh, soft clays and firm clays, hard clay, silt sand, gravel, and rock, we are going to use different samplers. Usually, tube samplers are used here. We can usually can go to SPT down to this level. Usually when you got in gravel, we may not be able to penetrate. Could be too hard. Then we would have to use the rotary drilling. And here, tube samplers for Shelby tubes could be used in soft soils. In hard soils, usually hard clays or residual soils, we we can use Denison, which I'm going to describe. SPT, maybe the maximum depth it would penetrate would be here. And then we're going to take the borehole down with rotary equipment and drill bit for rocks and take rock samples. So this is a very common, a very well-known figure of the SPT sampler. It was developed in the 30s in America, and it has an outside diameter of 2 inches, which stands for 50 millimeters. The inside diameter is about 35 millimeters, and it's a thick-walled sampler. This means that the material that goes inside is going to have lots of disturbance. So the quality of the sample that we get with the SPT is good for characterization, but not for tests, except at the bag limits, water content, things like that. And the other thing that's very important is usually in soft soils, SPT is very good to determine the depth of soft soil. These are kind of borehole log, as you see here. Uh, we have a soft soil of about 15 meters or so. No, I don't remember anyway. No, it's 6 meters, 6 meters depth. And then we have harder soils. As you see here, the SPT number is growing up. And usually uh, in soft soils, SPT is very low and it's not used. The only advantage of SPT is to determine the depth of the soft soil layer. And in general, we take the soft soil layer up to SPT number equal to 4. And what's this SPT number? It's the number of blows to drive the sampler 30 centimeters or 1 foot. Okay, so these are very standardized tests used everywhere and very important. But for soft soils, it's not the best because if any equal to 0, it's impossible to get, or very close to 0, it's impossible to get any property. Okay, and I'll give you an example. This is a correlation I used it a lot with SPT with uh, Young's modulus, or related to 50% uh, stress level in megapascals. And if you go under 10, this 10 SPT number 10, if you go below this value, the scatter is too much. So it's nearly impossible to get good property, a good value with very low SPT. That's why SPT is very important, but usually for harder soils. And so I'm going to describe a few samplers which are used for soft soils. This is the most common one. The tube sampler, the Shelby tube, is a thin-walled tube sampler. The fact that the wall is very thin leads to uh, good quantity samples that can be obtained with this, especially if the diameter is large. I've done many years ago kind of research that's part of my PhD thesis at the time, or no, MSc thesis, in which I carried out lots of unconfined compression tests and UU traxel tests on different diameter samples from different diameter samplers, as I'm showing here. I started with the 50 millimeter diameter sampler, a thin-walled sampler, 63, 75, and went up to 100. And as a result of this analysis, I could find very easily that the larger is the sampler, the better the results are. And I published this long ago in one of my books. And as you see here, the best quality which yielded the higher value of drain strength from these tests were the 36 millimeter specimen obtained from 125 millimeter diameter sampler. So we see here that usually we tend to use diameters above 75 millimeters. Under this value, there might be a lot of disturbance to the sample. Well, then comes, for me, is by far the best test, absolute essential in any project with soft soils, which is CPT. And the CPT is here. It's a cone, a cemented cone, in which we measure three parameters, and it's pushed into the ground statically by means of hydraulic system. The reference to these tests you may find online. One of them is the uh, uh, Peter Robinson's guide, which I use a lot. Also, this book from Fernando Schneider, a friend of mine. So you might be interested, and they are available. A little bit of history. Oh, sorry. The history, CPT history. The first one to carry out was in Barendsen in 1931 in Holland, and the Dutch people, why they have to develop something completely different from SPT, because Holland is a place of very soft soils. The SPT in Holland is mainly zero all the time. So SPT is almost non-useful in Holland. So that's why they decide to develop something completely different with static penetration, and they were very successful. And so 1931, the first one. Then Houtje. Houtje is Houda is a place in Holland where they make that famous cheese, Houda cheese, and also they used there was a mechanical factory, the Houtje Machine Fabriek, which made these cones, developed the mechanical cone. Vermeiden in 1947. Then the electrical cone came with Fulgro in 1964. The 1969, Bergman came up with this mechanical sleeve friction cone. That's the first time I've seen. I was in school of engineering at the time, and I was taken to a site where Frankie Pali was doing work, and they were using the Begman cone. It was my first visit to the cone. Then Torstenson did a lot of work on the piezo cone. He's probably the father of the piezo cone. Then UBC, from 1984 onwards, they developed the seismic cone, which I also had the opportunity to work with them later on. So this is the main history. I started, the first time I saw a cone was in 1979, and about 1975 was the first time I managed to carry out some tests with equipment that we developed at the time. Very bad equipment, I can say today. But anyway, the cone today has three, usually two or three separated load cells or gauges. One of them measures the most important thing, which is the tip resistance here, QC. Then on the shoulder of the tip, we measure U2, which is the pore pressure. There's a porous element here to measure the pore pressure at this point. And then we measure the friction along a sleeve here. So this is how mechanical cones are made. They have a sleeve, they have a load cell for the tip, a load cell for the sleeve as well, separated, and very important, the pore pressure gauge. Standards, there are many. But the SM standard is very good, and I always invite you to have a look at this standard. This is one of the best. Almost every country has a different standard, but this is quite good. GSM. Not all, as I'm going to say, not all American standards are very good. But this one is, and this was my first experience with CPT. I uh, I was doing my PhD at this time. I just finished my MSc in 1975, and there was someone, there was a colleague of mine, Camilo Borges, and he was working on the cone, and he carried out the first approach of cone testing in soft clays, and he used this at the time. We used this plotter. We didn't have uh, digital equipment. So everything has to be plotted, and the results were obtained from the plot. And it took a long time. I worked in Britain from 80 to 84, and at the time we used a plotter like this as well. Fugro used a plotter like that as well. So, but this very very old equipment. And today, what we use is very much more developed piece of cone, totally electronic, though the data are sent by electronic means. So, and we have these three gauges, one for unit friction, the other one for pore pressure, and the tip resistance. This is in 1994, about this time. This was the electronic engineer that worked with me, and he developed the electronics for the cone. I bought a cone from Hogan Togler, manufacturing in America, and we made the signal conditioning. But this guy made the signal condition. All we turned into digital cone, and this was a big development to the cone. And here's how the software worked. We have this graph here is the inclination. We had a gauge to measure inclination of the cone. This tip resistance, this lateral friction or sleeve friction, and this is pore pressure. So this made a big difference. As you can see, this was the first time in 1975, my first that test that I showed you in 1975 was carried out with this mechanical rig, very very rough mechanical rig that we used at the time. And later on, 1991, I spent 1 year working with Professor Campanella at UBC, and this was one of the main equipments that they had at the time, uh, which was the UBC truck, and we used to go out every, once a week to carry out tests on sites, different sites, and then we spent the whole week, the rest of the week, analyzing the results. And we carried out not only CPT, but we carried a lot of sizing CPT as well. I'm not going to address this because this is usually not very important for soft soils. And uh, so I had a marvelous experience to learn from UBC, from Professor Campanella at that time. And this is when we start to do tests uh, back in, I think, 1995. That's the kind of uh, equipment that we had available. We had the cone was digital already, and this was a portable equipment. And we did a lot of projects with cones in a few countries, like this dam in Ecuador. I was personally involved in that. We carried out the tests and we did the analysis, and we did the seismic analysis as well. Uh, Ecuador has lots of earthquakes, and this is some of the pictures of the time how we carried the cone, but we adapted a drill rig, an existing drill rig there, and it was successful. Also, we have done some projects on a few mines in Peru about that time, and this was the truck I was working. Well, what's amazing that looks like I have worked in this truck twice. One of them, the first time it was 1984. I was working at Fugro in Hemel Hempstead in the UK, and I went out in this truck to to learn how they used to do CPTs. And then it looks like the same cone, the same truck was sent later to Hong Kong by Fugro, and I happened to meet the same equipment in 1997, many years later, and we did a project at the World Olympic Stadium, something like that, in 1997. And this was by far the most advanced equipment I have ever seen. It was installed by this company, which I visited in 2002, and they have all these crawlers, etc., to move on soft ground, etc. Very sophisticated equipment. I've never seen anything like that anywhere. So I'm not going to spend a lot of time. Uh, we built this calibration frame to calibrate our cones. This part of the quality assurance specs or procedures. We also used this porous element saturation. We have two equipment. One of them was a sonic bath. This is something which is used in machine workshop to clean. So we used that to clean the porous elements. And then we have this compressor. This I've seen when I went to the dentist, and I've seen this equipment. I said, that's what I need to apply vacuum and to saturate the porous element. This big part, very important part of the job. And uh, then later on, I'm going to show you, I learned with Professor Campanella how to do a proper saturation of this cavity here by using kind of a cone. I'll show you more details. We put the liquid here. The liquid is uh, water and I forgot the name. Not water. I remember. Sorry about that. Uh, is something with something more viscous that we mix with water. We never use only water. Uh, could be I remember. Uh, And then what we do, we take the tip off and we use a syringe to saturate the element from inside out. Okay, and this the late Professor Campanella. Uh, he died a few years ago. He passed away a few years ago, and he taught me this and how to prepare the cone, how to uh, take off the tip, and how to do the saturation with this, okay, uh, and how to use the syringe to fill up the cavity from inside out, and then we use a condom. Always use a condom here to make sure that we don't lose saturation during handling. Okay. The other thing that was developed in BC, they came up with they found that the effects of nickel and areas. Professor Campanella told me a very interesting story. Is that Fugro at this time already knew that, but didn't they did not understand why. They used to do offshore tests, and they used to zero the cone before entering the going down in the water. And then when they came very close to the mud line, 100 meters or I don't know how many meters below, they found that the numbers were different on the screen. I mean, the measurements of tip resistance was different. So they have to re-zero the cone there. Uh, Professor Campanella had the idea of testing and testing and testing, and after some time he came up with the solution is that why you have this unbalance, because the areas behind the cone is different from the areas in front of the cone. Okay, so this ratio leads to an imbalance. Okay, this also happens when with the friction sleeve when you know some people uh, design the friction sleeve with this area different from the area at the top. So uh, this is easy to get around. It's just all you have to do is a constant area, constant, you know, the same area at the top at the bottom, easy to do. But for the cone, what Professor Campanella did, he put the cone into water, okay, and applied pressure, water pressure. And he found, as he raised the pore pressure, the water pressure, QC also raised. So he came up, this should be a perfect cone, and this should be, most of the cones would have behavior like that. And he proposed, and we used it a lot, that to correct the tip resistance, we call it the QT, is the correct value, and is a function of the measured QC, a function of the pore pressure, and 1 minus A, in which A is the area ratio between the top and the bottom of the cone. Okay, and this is usually in most cones. This area ratio is 0.8. It's impossible to have an area perfect area ratio would be 1. This is impossible to do. But this is we do one test once, and then we get this number, and we use for all the calculations. The other thing which is very important, and I uh, I had a lot of problems until I found the best way to take measurements. Uh, the important thing is to get very good saturation. And if you do a poor saturation, you can easily find out what's going on. If you see here, this is pore pressure versus depth measured on that position. We call it U2. I'll talk about that later on. And you see a poor response with wrong pore pressure values. And only we have a good response at this area where we see a completely different pattern of the. But only by looking at a plot like that, we see that the pore pressure is not very good. And this is something very important. And sometimes I receive data, I receive information with poor pore pressure data. This, for instance, is another case in which at certain depth, for instance, the pore pressure is very bad, up to 10 meters. And then beyond this depth, we get pore pressure saturation. And why do I know that? Because we see the small lenses. We see if you have uh, a seam or a lens, a sand lens, then you see what happens to the pore pressure. Okay, so this is easy to find. And when we have a very good saturation, that's what we get. And you see here, this is a sand seam, this is another sand seam, and we can see from the graph the quality of the saturation. However, there's something which sometimes is very difficult to do, is to get rid of, is cavitation. And what's cavitation? Cavitation occurs when the cone, here's the pore pressure plot, the cone gets into a very hard soil sometimes. For instance, here, or here the cone is, the pore pressure seems to go well, but when it comes to this very hard soil, this is a QT, then we may have cavitation. And when it's due to I forgot, I just remember the name of the liquid that we mix with water is glycerin. Sorry about that. Took me 10 minutes to remember the name. Glycerin and water. We mix them together and we use for uh, at the pressure element. And sometimes cavitation is nearly impossible to get rid of. Uh, this the, is a CPT we carried out to 30 meters depth, and I was unhappy. We carried out first this blue one, okay, and I was very unhappy with the loss of saturation at this point. And then, by analyzing the data, I asked the operator to do another nearby. And what we have done here to ensure a better saturation during penetration or loss or to avoid loss of saturation, we carried out a small borehole, let's say 50 centimeters depth. We filled with water, and then we started the penetration again, and we got red, this red line, you know, and we see here much better pore pressure results. Okay, so this is an important point. Stratigraphy. Let's talk a little bit. This is how it started many years ago in the 80s, early 80s. That's how we came up with stratigraphy. If we have this is tip resistance. If we in sands we have very high tip resistance. In clays they go back to nearly zero, very low values. Then we have another layer of sand. It goes up again, and then clay. So in the beginning, interpretation was only done by tip resistance. Then other methods came up, and they were developed mainly in Canada by Professor Campanella, Peter Robs, and others. And this is what we have test that we have done. I was uh, part of that. I was doing this test in 1991, and here we have the tip resistance, the friction ratio. Friction ratio, we don't use friction. As a matter of fact, we use the friction ratio, which is the friction divided by QT. And here the pore pressure. And then they came up with some idea by analyzing these plots. They came up with some ideas on how to do the interpretation. And first of all, how we do that? The easiest part is to look at the QT. When we have a high value, sand, definitely. And then it goes back. Here is clay. Here we may have some sand seams. So we have an increase in the QT due to these seams, and we go down to 70 meters. It was probably the deepest CPT I have ever done. And here we have the ratio between the uh, friction ratio divided by QT. And what we see very clearly is that low values usually related to clays and high values related to sand. And this is silty clay, so it should be in the middle. And also we can look at the pore pressure. If the pore pressure are good, this is very good measurement. These are very good measurement of pore pressure. And we see here, very interesting. The pore pressure goes down to the static case where when we have an increase at QT. So it's very clearly a sand seam here. So this is kind of interpretation we could do with these data. But this evolved. No? This was the how we used to do at that time. These are another uh, 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 another CPT I have done many years ago, and where we have just the opposite. We have here a clay seam instead of a sand seam. We have a clay seam. This is mainly sand with a clay seam seen here. But uh, everything changed when people started to use these kind of plots. I mean, QT, the corrected tip resistance against uh, friction ratio. And here, different type of soils that can be used. At the same time, this was done by the Norwegians. They used the Buki, which is the pore pressure parameter. This is very old. And the pore pressure parameter Buki is defined by U2, the measured value, hydrostatic value, QT, which is the tip resistance, minus the total vertical stress. So uh, it, I remember very much some people from Norway saying, "No, this is very good, etc., etc." It's not. And why? Because in those days they were using a very good pore pressure measurement from offshore tests in which we have a very high water pressure. In many cases, on land CPTs, we may not have the same quality of pore pressure measurements because of the loss of saturation, cavitation, everything. So today, I think this kind of plot is not reliable for uh, interpretation. On the other hand, Peter Robson did a marvelous work. I think he started with Campanella, then he moved to Alberta, and he came up with this soil behavioral type, which is more or less the same as before, QT vessel friction ratio, the same as before, but he put different color, normalized color behavior in order to for us to easily see what type of material we are working. And the first the first soil behavioral type classification that he came up, QT was in megapascals and friction ratio in percentage. Later on, this evolved, and uh, I'm going to show you how we do today. And usually CPT it has an enormous amount of data that takes a long time to to process. Uh, while I was in at UBC, we used to spend almost 1 week, 4 days at least, working on the data that we got in Monday field work. And but today we have very good software. For instance, what I use is the CPT, this one here by a Greek company called Geologmistic. I use also Sleek for earthquake analysis, and I use this a lot, and it's very helpful and makes the analysis very fast. And so in 1991, we didn't have this kind of software, and what I used was Sigma plots. was a software that I learned how to do. We have to program the sigma plot. I learned how to do that. So in 1991, uh, this was the best that we could come up with. Uh, so what we see here, very homogeneous soft soil with no sand seams, and why? Because pore pressure doesn't show a drop, and so uh, let's go ahead. And today we use this software, and this software is fantastic. Uh, we can do many CPTs. We can analyze many CPTs in one day. I helped also to develop this kind of software by testing, by coming up with some ideas. But of course, Peter Robson was the main developer, or he came up with lots of ideas. I worked with this uh, Greek company since the beginning, and this the corner resistance, friction ratio, pore pressure, and SBT indicator, solid behavioral type was the classification that Robson proposed, which is very good. And also, this software enables parameter estimation. Lots of parameters can be estimated with the software, and like the constraint model, shear strength, and drainage strength ratio, OCR, etc. And deformation models. This is very important. This is the first attempt by Yambo to come up with deformation, one-dimensional deformation models M, and we can we can come up with Young modulus also with a correlation like this. Shear modulus also a correlation. Of course, the alpha values are different: alpha 1, alpha 2, alpha 3. And later on, the first the first published, as far as I understand, to obtain this kind of models from clays was by Sanglehar. He wrote a book, a very important book on in French, and he came up with these correlations, which are used in the past. Later on, we have this by Kuhari Main, 1990, for many different types of soils, from sands, etc., sands, clays, etc. Everything fits into an equation like that. And but later on, Peter Robson did a very good work. He improved this kind of correlation, the same type of equation, but he separated from different types of soils. For clays and for sands, and alpha became can be obtained by this equation. And the CPT, the software I use, does it automatically. And what we get, settlement calculation QT, it estimated M, and then we can come up with settlements through this very simple equation. And I do this a lot, and I can assure you, I have done yesterday a very interesting project with that. And the difference between using the laboratory tests and CPT was enormous. The guys who did the calculation came up with a settlement. It's a 8-meter high embankment. The settlement was they calculated something like zero 0.8 meters of settlement. And my calculation, which I believe very much, it's a very reliable calculation, was about 3 times more than the guys calculated. And I'm sure from experience, I can assure you, this is by far the best way to obtain settlement calculation from CPT. The other very important thing, but not so easy, is the dissipation test. As we stop the cone during penetration and we observe the change in pore pressure, that's when we have a kind of dissipation. Dissipation can be uh, decrease in pore pressure, okay? Or sometimes if you are in an over-consolidated soil, you can have an increase in pore pressure if you stop. And here is when you don't have dissipation at all, because you are in a sand with a high permeability. You don't have any dissipation. So that's the case. So uh, how can we explain the dissipation by take into account dilation and contraction. So if you have a sample in a Traxel test that dilates increase in volume. What happens that if the sample is saturated, the particle will tend to come out, to go to dilate, and then the pore pressure would decrease. So it's a contrary effect. Just the opposite, the contraction. If the sample tends to contract during shear, what we have here, let's see, consider 4 particles in the motor here. So we may have a decrease in volume, and this is going to lead an increase in pore pressure. So the more pore pressure you have, the more possibility of contraction. It's a contractive behavior. On the other hand, if the pore pressure goes down, you may have a dilated behavior. Today, these concepts are very important, especially in tailings, and this is what leads to static liquefaction. Okay, these are different types of pore pressure elements that have been used in the past. Uh, very old. I don't remember who it was used in Holland. This was used by Torstensson. Fugro, when I was in Britain in 1884, they didn't use the pore pressure element in the beginning. People were. I remember I attended a conference at the civils in the Institute of Civil Engineers, at the Institute of Civil Engineers, in which they were discussing. There was a very interesting discussion about whether or not to use pore pressure measurements in the cone. Some people were not convinced by them. And today, what we what we use is this. Most cones do not have this pore element here. They have in what we call the position 2. This is compulsory. If you want to have another porous element, you can, but position 2 is compulsory. So we have, that's why we call this U2, because that's where we measure on the shoulder of the cone. In order to analyze uh, analyze this behavior, there are many theories, and what we use is Hosby-Thiers theory. We came up in 1988. Is for cavity like a pizza cone, nonlinear model, 2D, and any index, rigidity index like this. Okay, so that's what I use. This is also used in CPT. And how to do that? To extrapolate the line. This is a dissipation plotted against square root of time, and we draw this line, tangent line. Okay, we obtain U naught, we obtain U100, then we obtain 150, which is the middle, and going back in the middle, we obtain T50, and this T50 is used in calculations, and this is an example. This T50 is fixed due to the theory. O245, R2 is the diameter, the rigidity, which is obtained by these values. If it's 100, so the calculation would be 336 square meter per year. Okay. Yesterday I was doing this project, and I had access to these horizontal coefficient consolidation obtained by the cone in a few tests. This is a project in Guyana, a very large project. And as you see here, we have a lot of scatter. The values here of CH vary from 0 to 100. So I decided to use a conservative value, which is just in the middle of these points that I have here. This design decision is not easy. Sometimes the scatter is so large, which is difficult to assign a value. And then what I do, I base my choice on experience. And these are many sites, soft clay sites in Brazil, in which I have experience. I have all these values plotted. As you see, there's a very large scattering. Most of the most of the sites. This one, why it is so large? Because it's an alluvial clay, and these are marine clay. Marine clay tend to have lower values than this alluvial clay. So uh, when I always when I have a project, I compare the results here, and then in order to select a proper value for further analysis. In addition to that, we have to correct for the different drainage path because the cone measure in the horizontal direction, and we have to measure. We have to for time rate calculation settlement versus time calculation. We need CV, which is the vertical direction, and we still have to correct. There are ways to do that. I'm not going to discuss this too much, but usually if you divide by 4 or 5, you're not very far from the right answer. Okay. Uh, okay. Let's make a 2 minutes break. It's about 1 hour that since we started. Let's make a 2 minutes break, and then we are going to discuss. Uh, we're going to discuss uh, Venshi. Okay. Just a second. Well, let's go back. Now we have a brief discussion on the vein testing. Uh, a little bit of history. Uh, it started with Olson in 1919, just after the First World War. And then Scampton did a lot of work in 1948 when I was born, so 76 years ago. And the first test in Brazil was very interesting. They were carried out by one of my professors at School of Engineering. Uh, they started doing that 1 year after Scampton, just after the war, and two people did this more or less the same time. And I I was a student of Dr. Raimundo Costa long ago, and he was the first. And he told me a lot of interesting things about the test. In 1950, the Swedish Geotechnical Institute came up with a very interesting development of the equipment, which I'm going to address. And from 1974 to 1980, I worked at the soft soil research program carried out by the Road Research Institute in Brazil. And I was a very young research engineer. And that's where I did my MSc and my PhD. It was a very interesting, a very comprehensive research program. And we did a lot of tests, and I'm going to address that. This is the traditional equation that came up with considering well-distributed rectangular distribution of stresses throughout the vein. And later on, 1984, Peter Roth from Oxford, did a lot of work on that, and he came up with a different equation, slightly different from that, with a different distribution of stresses along along the vein. However, in the end of the paper, although he did a lot of work, he recommended that we should keep the old equation because that's where the experience came from. And this old equation, the strength is related to the torque to 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 move the vein, the torque value, and the diameter of the vein for a vein which is twice the height is twice the diameter. Okay, and usually this is what we measured during the vein testing. We did a initial test rotating the vein, and you have the undisturbed value, and then we do another test after remolding it. We turn the vein 10 times. It varies according to the standard, but we turn the vein 10 times to get a completely remolded value of strength, and you do the test again. So we take these values of torque and we enter that equation. And in 1985, I did with a very good friend of mine, who is Harold Collette, and we did a equipment classification because we found out the vein in those days, the vein results could be very dependent on the equipment. We have this, what we call the C type, in which we have a lot of friction here. The test is done in a borehole, and this was used for many years. Then we have this different B type, which the rods are protected against friction, like here, okay? And we have the A type, in which we may have a torque measuring device. In those days, we didn't have that, but today we may have some equipment with a torque measuring device. Is could work well. So we get rid of the torque above, and we may have, this is what we have done in the past, the kind of was originally suggested by the Swedish, and we designed something like that to have the type A, and I show you why. So the equipment types are, first of all, we have the unprotected vein in a borehole, unprotected vein, but the rods are fully protected, so no friction on the rods. We have unprotected vein, unprotected rods, but you can have a torque load cell, a torque cell, and protected vein and protected rods. When we did this work, this was our choice because we didn't have the torque cell, a good torque cell at the time. And this is the kind of results we did. We went to a site not far from Rio de Janeiro, and it's a very soft clay. And we did. I remember some 10 boreholes, uh, taking measurements, torque measurements, and this is what we got: very large scatter for the results. And why? We found out we have the problem of the torque, we have the problem of translation. The vein would present a translation, so these problems would affect the measure values. The other thing that we found, in those days, the STM standard suggested that we could determine rod friction by not using the vane like this, okay? And what we found, it was nearly impossible to do this kind of correction. Why? Because the results were totally difficult to understand. For instance, we have a 2 meter torque here, 3 meter torque here, 5 meter, this is the depth. And very difficult to find out what would be the torque. So uh, also the torque had the friction would have a tremendous effect. The equivalent CU from these friction measurements would be 2 to 4 kPa. It's almost half of the strength of that clay. So we decided that equipment was not very good at all. This was 19, 19, I think 1980, 1981 technology. We decided to carry out a complete redesign of the equipment, and I found out a mechanical engineer who happens to be a friend of mine, and he helped us to design a completely redesign the equipment. So the rods were totally protected. They had bearings to avoid friction, and the vane would go into this protection shoe. This was the Swedish idea which we used. It was a steel protection shoe. Then the vane came out, did the test, and went back to the protection shoe. He designed also the better without unity, and we used this, and the results were completely different. I remember we carried out 6 boreholes very close, 2 meters apart, and the scatter is much less, okay? And this, we did 6 boreholes, and this remolded value. So the scatter is much less than the other one. And if we compare the two results, we see this is higher and much less scatter. And what happens that I presented this paper, that paper we call in conference, in SM conference, I think it was 1985. Yeah, 1985 in Tampa, Florida. I went there, presented the results, and we condemned the idea of 2 things that were very clear from that conference. First of all, we have to standardize the vane, because if you very different diameter and also the shapes, we may not have a standard for the vane. And this test is partially empirical. So that's why standardization is so important. But the worst was that in that standard, we told people very clearly that rod friction measurements under no loading condition cannot be performed. Cannot. But still, they keep it today. In the standard of 2018, they're still there. And I think it should be changed. But since 1985, despite of the conference that I attended, lots of people agreed with that. Nothing was done to this standard. So this is the kind of results that we got with this vein. This is the type of clay that I was doing this kind of research. This liquid liquid limit very high. The average PI is about 70, so very high, etc. These are the understandable values. Let's go ahead. And then there was a big discussion in those days, started, I think, 1972 by Bierron. Bierron was the first to address this, was vane correction. He came up with the idea that as a function of IP or PI, persistence index, we would have to correct the vane shear strength empirically. And this he was the first, 1972. Then some other people came up with some ideas, etc. But the problem is, it's not an easy task to do this kind of correction. And then what people tend to use today as a vein correction factor, in order to get a factor of safe of 1, is to correct the value by multiplying field values by zero 0.7. And that's what I do. Okay, I don't. It's the scatter to use these PI values could be very large. So if we use zero 0.7, is we may get the correct answer. The other thing is that these are is another site that we carry out lots of field vein tests, very good one, very reliable with the good equipment, and still you have a lot of scatter. And then you have to decide what shall be the design profile. If we use the average, we may be very far from the this the average, and this is what I have used. These are design decision, and you still have to multiply this by 0.7 to get the results. That's what I usually do. The other thing is that I have a database from many projects that I have worked, and this is the strength ratio divided by the effective stress against depth. And this is, if you use something like 0.22, which is should be this dashed line here, you always be right. This was 0.25, should be okay. And if you use larger values, you have to test. Okay. And also, what I always do, I do a kind of calibration. I always compare the results from vein testing, this vein testing undisturbed, with the values that are obtained from the cone through correlation, from the piezo cone. This is very important. To at any project, you do combine CPTU, and uh, vein testing, and compare the results in order to calibrate the correlation we are going to use in the cone. This is very important. And here's the kind of calibration that I have done in one of my projects. Uh, Finally, in terms of investigation, how much should you invest in site investigation for a project? Okay, so this total increase in construction price, and this is the site investigation investment. Okay, so if you invest, let's say, uh, 1% of 1% of the, let's say he's 2%. If you invest 2%, you still may have a lot of construction costs, additional construction costs. It could be nearly 60% of the initial investigation. This vary according to the type of structure, but in, also the risk. For instance, in dams, we should invest something like 3%. That's the target. In tunnels as well. In soft clays, the minimum should be 0.5% for embankment soft soil, because the risk is lower than tunnels and dams. Okay, this should be the minimum of investment. You should always take that into account. Well, let's have a look now on solution ground improvement areas. So, ground improvement, we have here this plot with particle size against percent finding by weight, and here you have gravel, sand, silt, clay, and here are all types of ground improvement we may use. But I'm going to talk only about clays and silty clays, and we're going to talk about this. And tri embankments. This is the way that I've learned. I have worked through my life on all these tri embankments. Okay, the first one, 1975. I didn't design, but at some here, those embankments here I have designed. This as well. Yeah, I have designed all these embankments except the first one, and we learned a lot. I'm going to address a few of them. The first one, very interesting, trying back to stone column. That was 1975. I was very young, and I just finished my MSc, and I was involved in this embankment, not to design, but just to install the instrumentation, which I have designed for my MSc thesis. This was a site at the harbor here in this area south of about 100 kilometers south of Rio de Janeiro, Sepetiba Harbor, and there was a big project to expand the uh, uh, the harbor backyard, and we had these are the soil properties of that clay. You know, high Pi, gamma is about 14 kilonewtons per cubic meter, and here's the endurance strength. It's over 20, so it's not very soft. Okay, and these were data obtained by VST at the time, but these VST may have been affected by rod friction, which in those days we didn't we didn't realize as much as we do today. And there was an Italian company that came to Brazil in those days, and they proposed stone column. And the designer, which was a big company, Planavi, they decided to accept the idea, and Planavi designed an embankment to test these stone columns. These stone columns were made with casing. They installed a casing. The case diameter was 520 millimeters, installed with a vibrator, and they tested column spacing from 2.5 meters to 3 meters. So the installation method: install the casing, fill up with gravel, and then use a vibrator at the top, a big vibrator, remember, to extract the casing and leave the column ready. Planavi designed an embankment like that, up to 5 meters of height. In the soft clay was 15 meters. And so to test this, I helped with the instrumentation. Why? Because in those days I was working at the Road Research Institute, and I have designed and built several hydraulic piezometers, hydraulic twin tube piezometers to use in the research. This is 1980 technology, so we used mercury manometers to do that. Today is a nightmare. No one is going to use hydraulic piezometer for a job like this. But in those days, that's what we decided to do. And these piezometers were very successful. This is the equipment to the piezometer, very complex. I'm not to talk about that because no one is going to use hydraulic piezometers anymore. Today we use vibrating wire piezometers, much better. But despite of all efforts they have done, the settlements with stone columns were very close to no ground improvement. They had two embankments, one of them on stone columns, the other one without. And so the designer decided not to use this solution for the stockpiles of the harbor. And then lessons that we have learned from this embankment. Stone columns were not efficient due to small diameter casing. Today we use much larger stone column diameters, about 900 millimeters, and also very large spacing on 2.5 and 3 meters. Today we can do some calculation I have done recently just to check, and today we would understand that. And the other installation method, which evolved a lot along the years. So much later on, this kind of bottom feed development was developed, in which the gravel installed from the bottom and is vibrated with this equipment. So we get much better column, large diameter, and well compacted stone column. So fast installation rates, less soil disturbance, better gravel compaction, and better for column continuity. If we extract, we may have something like that, which would not take place with the bottom feed. Bottom feed doesn't allow this to happen. Okay, this is not enough. The same when I was working at the Road Research Laboratory, and we designed these embankments later on. We decided, first of all, they wanted to test soft clay. So we found a site not very far from Rio, and this research took place from 1974 to 1981. So what we did here, we did three different experiments, field experiments. The first one was the embankment one, which was taken to failure. That was my PhD thesis. And then I continued working on that. We did the access road, which I'm going to show you. For the first time, we test geosynthetics uh, under the access road embankment. And in those days, there was a lot of fuss. Which type of drain should we use? Wick drains, jetted drains, open mandrel, closed mandrel. And then I designed with some friends this embankment too. So we had sections which were 40 meters wide by 40 meters long by 40 meters wide. We have all these sections, and they were fully instrumented with piezometers, supplement device, etc., to test the embankment. This was the first embankment, which was my PhD. It failed on 7 December 1977. It was a very interesting experience. And later on, I did a lot of analysis with the technology which was available, of course, in those days. Very difficult to run programs. We didn't have PCs, only mainframes, very difficult. But anyway, we did a lot of analysis and we found that using the mean value of the vein strength, we could get a factor of 6 not very far from 1, which explains the maximum height that embankment reached, which was 2.8 meters. Okay, and lessons. The maximum height was 2.8 meters on that clay. Back analysis, which mean uncorrected field vein strength, yielded factor of safety not very far from 1. Biermann correction in those days, we found it would not apply. Although today I would prefer to apply to be on the safe side. The field vein equipment was improved to avoid friction and translation of the vein, and all instrumentation was locally made. I designed almost everything except the inclinometer, which was bought from slope indicator at the time. And this was the embankment too, full instrument with vertical accessometer, magnetic accessometer, inclinometer, lots of settlement plates, and horizontal accessometer as well. And we tested, because this was the main question. Could sand drains be used in those days? What was the best, wick drains or sand drains? Then this was tested in this embankment. And we used the open mandrel method, okay, with Frankie type equipment. And we used the jetted sand drains, which was used in those days by jetting, water jetting the clay in order to create a borehole. And we used the wick drains as well. Not the technology that we use today, but it was what was available in those days. And also, we had a very bad idea to try to use non-woven geosynthetic wick drains because we thought the water could come out of this, and it was a failure. What we found later on is that the vertical permeability along the geosynthetic wick drains is very small. Only the horizontal permeability is high. So, but anyway, we tried and we tried and we tried and we learned from the mistakes. But the mistakes were made on a trial embankment, not the construction itself. So, pop pressure measurements, what we had, the closed mandrel led to very high pop pressure in the clay, the open mandrel less, the jetted drain not very high, and the geotextile and wick drains have the best behavior in terms of pop pressure during installation. And settlements. So we measured settlements in all these sections. We could compute, and what we found, very interesting from the experience. I'm not going to give you all the details, but we found the jetted drains increased settlements by 40% because this soil disturbance. We didn't know that. Sand drain increased pop pressure a lot. Okay, Non-woven weak drains did not work at all. And composite weak drains yielded the best results. So these were the lessons that we learned. And then we did the access road, which was an access road in order to bring the material to the main embankment. And this is the access road design. It was only 4 meters wide for the trucks to pass. And then manufacturer of geosynthetic manufacturer, the first I ever met, they came to us and gave the material for us to test. So we applied the material, the geosynthetic here, in order to test to see whether or not it was a good idea. And this was my friend, today Professor Emeritus Palmeira, but this was 1981. It was his MSc thesis. And we used a non-woven geosynthetic, 400 grams per square meter, but the strain at failure was 30%. I said, it's not going to work. Why? Because the strain at failure is too large. Okay, let's test it. Let's see. We did sections like this, how to stretch, different ways of stretching the geosynthetic under the road. We did like this with anchor, and we did like this anchored. And what we found is that geosynthetic worked. Despite of my initial belief that it wouldn't work, they worked very well. And the lessons were: settlement measurements were from 100 to 200 millimeters. Measured strain were 10%. How did it work? Because when the geosynthetic has horizontal pressure over it, the strain at failure is much less. And bearing failure occurred at the control section without the geosynthetic. Reinforcement effects after 200 trucks passed. So the reinforcement were prevented bearing failure, reduces settlements by 20%, okay, and reduced embankment volume by 20 to 25%. So what my previous beliefs were totally wrong. So testing, testing, testing. This is necessary, absolutely necessary. And then we did this dam. I was invited by a friend of mine who was the main designer of this dam. It was 150 kilometers north of Rio. And they have, this was sand, no problem with the foundation, but that was 1 kilometer of a dam. It was not a very high dam, 12 meters high, and a lot of soft soil. So they invited me to carry out this tri-embankment, and I designed this embankment, and we did a lot of work here to understand the behavior of this embankment. And these were the properties I'm not going to talk too much about, but we had some layers with peat in addition to clay. We carried out all these tests, vein tests, lots of laboratory tests, etc. And then this was the design decision that has to be taken: to burn or not to burn. And this had a very high implication on the cost and also in terms of risks. So that's why the designer invited us to work on this. The dam was not very high. And we did the straw embankment, full instrumented. Now we had a lot of experience with instrumentation from all that experience, all the tri embankment before, and we did the best we could. And this what became the PhD thesis of one of my friends, who also is a professor of soil mechanics, and he did this analysis. The lessons here were: slip surface located through instruments. We had lots of instruments to locate the slip surface. Mobilized mean drainage strength at failure was about 20 kPa, so this was the key parameter for the design. Key information for the dam design, this parameter. Okay, and why weak drains and temporary surcharge work so well? And this was by far the best method in that embankment, tri-embankment 2, the best behavior was weak drains. And why? Let's discuss this. Well, after that experiment with geotextile, etc., we came up with the idea of always using a geotextile in order to protect the sand blankets, which allows the water to flow. Okay, so in order to ensure continuity of the sand blanket, we always should use geosynthetics, and then we install the weak drains. We're going to talk about that later on. When we have high embankments, we use geogrids, which has shown to be a very good uh, instrument to avoid failure, to ensure safety, to ensure that's not going to fail. Then we put embankments, we put a temporary surcharge, and after a few months, usually 6 months, we take it off. Okay, and we did lots of projects like that. This is one of those in the north of the country. These kind of weak drains, very good one, and so we have here some measurements during application of surcharge, settlements. Here's embankment height. These are settlements. So surcharge was applied, the embankment height plus a surcharge. Then it lasted for some time. And then there was some additional surcharge available. We put more, we raised the level of surcharge, and then it was removed uh, after nearly 180 days of elapsing time. And what we saw here is that removal led to we continued to take settlement measurements, and the removal shows here that settlement stopped. While this is another section in which the surcharge was not removed, then we still had a high rate of settlements taking place. So removing led to stop settlements. And here's when surcharge remains. And the pump pressure more or less the same. Here we used vibrating wire piezometer, so very reliable readings and very easy to install. When weak drains were installed, surcharge was applied here. When we apply the surcharge, we see the pump pressure builds up a lot, but in in 30 days, 40 days, the pump pressure drops. So it shows that the drainage system is working very well. So it shows the weak drains are very efficient. And here, uh, we had some material to increase the surcharge, so that was we have done. And here, for some mistake, this was a mistake made by the contractor. He put some, he stored some additional material, 2 meters, at this section. And what happens? The pump pressure built up very quick. And when I saw it, no, we have to take it off immediately because I was afraid of a failure. No failure took place. But anyway, they removed and the pump pressure went down. And this I have been to this place many times. It's a nice place around a lagoon in the north. And I have been there 5 years, 10 years, 15 years, and we don't see any defect, despite of the fact that here we have nearly 12 meters of soft clays, very soft clays. Okay, and lessons from this experience. Uh, First one is how to avoid disturbance of the clay to keep the cross section of the mandrel less than 70 centimeters square. And this is what I wrote. I wrote many years ago one of the standards for the highways department, and I used that number, not more than 70 centimeters square. Also, this you have to ensure that sand mat has a very good drainage, and thickness should be over usually more than 40 centimeters. And we always use a woven geosynthetic here to ensure the continuity of this mat. The other thing is, if you have a very wide embankment, water may not come out. So you have to design drainage One of the projects that I'm working today is a very large area. So we have a drainage system with gravel. There's sand, then sand, say 30 centimeters. We have 20 centimeters of gravel and then sand again. And then we ensure drainage. The other possibility is to use these tubes, which is provided by manufacturers. So we have a drainage system here, the tube that allows the water to come out of this. I've seen lots of projects in which the pore pressure built up in the sand mats. Why? Because they didn't have a proper drainage. And finally, weak drains. Usually, what I like is to have is spacing of weak drains from 1.2 meters to 1.8 meters. Why? First of all, there are lots of information about when you push a pile into the ground. What's the effect of disturbance? Usually is 10 diameters. That's the all the clay around tube pile would be affected until 10 diameters. That's the spacing. So if we say that this is about 100 millimeters wide, so I don't like to go less than 1.4, 1.2 meters. I'm just working on a project that the design decided to with 0.9. Okay, uh, I don't use. I use usually uh, minimum would be 1.1 meters, but 1.2 and 1.8, you'll be right. Beyond 1.8, everything may not work. So that's why I think the uh, average value should be 1.5 meters spacing, and not. I would recommend not to go less than 1.2 meters. Tensile strength also is very important, not to avoid, not to break the weak drains. And drainage capacity, there are some research about that. I just use the values which have been recommended in the literature, but we make sure that the drainage capacity is 1,000 meters, cubic meters per year. Okay, so, and few sand seams. You have lots of sand seams, no need of weak drains. This is another project that I did in Porto Alegre Airport, and also we carried out very soft clay. We have 8 meters of very soft clay, and we decided to use, that was Keller had a contract to do deep soil mixing. And I was involved in the project to analyze the behavior of the embankment, the tri embankment, and this the mixing plant and quality control. They did a lot of unconfined compression tests on samples, and this was a tri embankment in which we have settlement plates, we have some earth pressure cells, piezometers, etc. And I did some analysis. I'll show you what happened was this was very important. This was designed to have a much lower this unconfined strength against time, okay? So the mix would increase depending on the cement type, and the design value was 1.35 megapascal, the unconfined strength. However, in order to reach this, the laboratory test they have done showed that they need much more cement content in the mix than they expected initially. So the lessons were uh, which I learned. DSM has a very high production rate of 5,000 meters per machine per month. So if you want to do any treatment very fast, DSM may be the answer. The embankment had a very good behavior. I'm not going to give you all the details because of lack of time. And the early estimated cement consumption was 150 kilos per cubic meter. This was a surprise because the actual needed, according to the tests they have done, was much higher, 350 kilos per cubic meter. So this, in order to analyze the cost of a project like that, you have to be very careful about cement consumption And the only way to do that is about testing, testing, testing. Okay, and need for initial dosage studies. Sometimes, even if you do a lot of dosage studies, you may you have to take actual samples from the columns and study that in order to come up with the ideal cement consumption. Well, final final step: lessons from someone else's errors, which I've seen and which I learned. It's very nice to learn from someone else's errors, especially in a construction site. And one of them was light embankments. Okay, light embankment is something that if you use EPS or geo, these EPS are plastic blocks, and they have a very light unit weight of about 1 kilonewton per cubic meter, so 10 times less than water. Okay, and this is a site in the north where a friend of mine have designed a piled slab for the approach embankment on soft clays, but then consultant came up with the idea, no, let's use EPS. It's much better, much faster, cheaper, etc., etc. But he forgot something very important: floods. And uh, it, I was told by this friend of mine that once there was a football game in another city, they had to cross this river. So lots of people went to watch the football game. And on the way back, just before, there was a very heavy rain and it was a flood at the abutments. And what happens? All these EPS or geopor, they floated and destroyed everything. So uh, you have to take care about that. I have other projects which I feared about floods, and I've seen design like that. Just by fearing about floods, I decided not to use for safety. Okay. The other thing which I've seen many times, people put a new embankment and forget the old embankment. So when they put the new embankment, there's a crack due to differential settlements. So if you are going to design something to enlarge a road on soft soil, either you take care of the settlements, make sure that you don't get lots of differential settlements in between the new embankment and old embankment. The other thing which I've seen a few times were early surcharge removal. Okay, in order to we have to inaugurate this road, this project, etc. And these are projects they removed the surcharge while they still had a large rate of settlements. So these are big mistake. The other project which I learned from someone as was pilot embankment. Pilot embankment works well if you do it right. And you put the piles in, you put the pile caps, you raise the embankment, and you put geogrids, embankment, and it works. I've seen this work many times. Okay, it's not cheap because one of the problems is the rate of installation of piles is very long, takes a lot of time. That's why DSM is much better, much faster. And this is a pilot embankment which I was invited to analyze the reasons for, of the failure. So the construction with concrete piles being driven. This is the pile cap. And when I was invited to the site, the pavement was like a roller coaster, with lots of undulations due to settlements in between the piles. And we did lots of excavation, and what we saw, all the geogrids were tore down, they were damaged here. And it was a disaster, a complete disaster. Later on, we learned uh, that this should be the proper way of designing it without sharp edges and a lot of protection in order to protect the geogrid layer. Okay, if we put the geogrid here, no problem, it's completely protected, but that design was very bad. The other thing which I learned from others' uh, mistakes was vacuum consolidation. Vacuum consolidation works very well. It works in many places, in many countries. They do it a lot in Holland, and it works provided you don't enter. You should take care. First of all, you must make sure that the vacuum works. There's no leakage. Second thing, you should not have a lot of sand seams. If you have sand seams, you're going to pull out water from the sand and not from the clay. Also, the weak drain should never go to the end, to the bottom of the clay, because then you may pull out water from the sand here or the other material that's underneath and not from the clay. So in order to do that, you should do at least a try embankment. You should do a much better site investigation in order to get the this position of the bottom and not to drive the weak drains to the end. And this is exactly what has not been done in this project, in which the pore pressure, they measure pore pressure while they were putting embankment. And the pore pressure, instead of having dissipation, the pore pressure increased. And they had this kind of failure that took place, which due to the fact that they did not carry out experiment before. So a project like that, you have to ensure that vacuum works, control leaks. Weak drain should never touch the bottom of the high permeable layers, the bottom of the clay. Okay, never. No sand seams. If you have a lot of sand seams, it may not work. Much better site investigation. Okay, and especially trial embankment is needed. The final topic is instrumentation monitoring, which I'm going to address very briefly, which measure are necessary settlements, horizontal displacements, and pore pressure. And this is the kind of instrumentation layout we always use. We have vibrating wire piezometers installed in the foundation, inclinometer at the edge of the embankment, settlement plates. We may have more than lots of settlement plates as well. And if you are doing weak drains, you always need to check the water pressure in the blanket to make sure it's zero. Okay, and different types of piezometer, standpipe piezometer we use in only in high permeability soils like sands, etc. You cannot use this in clays, as I have seen people trying to use this kind of piezometers in clays. Doesn't work. Stability control. The best method by far is by looking at the inclinometer results, and this is displacements that we have, and this is the rotation which the inclinometer measures directly. Okay, so if you have a very high distortion, that's when you're approaching failure. Distortion needs to failure. And why? Because let's imagine this is the inclinometer before and after you put them back, with that inclinometer you are measuring this kind of distortion. If you imagine the slip surface here is more or less horizontal, then this element is, we are measuring theta, and beta, which will be the angle here at the bottom, is zero. So that's why the strain distortion of the strains at failure, distortion strain at failure is equal to the measured value of the inclinometer. So if you measure that, it's a way of looking at what's going on in terms of stability. And this is that strain in relation to the relative height of the embankment, showing that severe cracking is when the cracking started. Okay, severe cracking took place here, completely failed when this value reached, say, 10% or a little bit less. Okay, distortional tilt. In this embankment, I had several inclinometers, and I happened to locate the slip surface through the inclinometer. And then we are coming to the end of the talk, and let's talk a little bit about philosophy. Physics versus soft soil engineering. Okay, uh, Einstein, Einstein, he proposed a new theory. Okay, and then many years after, someone comes up and proves he was right. He was right in many things, and I think soft soils engineering is quite the contrary. And why? Because in my humble imagination, I imagined lots of solutions that should work and didn't, and some which I thought would not work at all worked very well. So uh, the answer to software engineering development is testing, testing, testing. Don't imagine a lot of things because if you do, you may be wrong, as I was in my life many times. But the only way of being sure is to do testing. Never try a very big step. Do it in small steps as you learn. So, conclusion from our talks, they are uh, first of all, comprehensive site investigation, in which essentials are CPTU and VST along with laboratory tests as well. Okay, you have to do some laboratory tests, but the essentials are CPTU and VST in soft soils. A comprehensive monitoring program. Uh, we didn't discuss a lot, but I just gave you some ideas. Theories have to be validated. There's no theory. I've seen lots of theories which were not useful. Okay, avoid intellectual arrogance, and this was the main cause of some of the mistakes I have shown you here. Some professors coming up with very good ideas. Let's do that, and they didn't have experience, so the the uh, uh, improvement method did not work at all. You should be humble, a humble approach. Try embankments for large projects. Every time you have a very large project, design a try embankment. So that's it, my friends. Uh, these are my contact details. If anyone wants to any information or any question, or even if you want a copy of those books, I could send you. And I'm here to if you have any questions, I'm available to discuss with you. Okay. So no question came up yet, but if you have either the Insight Engineering Hub email, you can send them a question, and I'll be very happy to answer in writing. Or if you want copies of the books I have shown you, just send me an email or to Insight Engineering, and I'll be I'll send you back a copy of those. Okay, PDF copy. Anyway, thank you very much. I hope that you enjoyed the presentation. Thank you very much. Ah, there's there's a question here. If you have any suggestion for the best foundation system? No, it varies according to the ground conditions and of course loads. For instance, if you're dealing with bridges, you're going to have a usual bored piles. They should be very large diameter, 1.5 meters, 2 meters. Uh, I have Shu Sensai. Yeah, Shu Sensai. I have worked. I'm still working for the Chinese contractor CRCC, and I have designed two bridge foundation for them, and They used nearly 2 meter diameter piles, so they are very deep piles, down to 100 meters deep. So it varies according to the problem that you have. If for normal buildings you're going to have much uh, uh, the piles are going to be much less deep, say 30 meters or so, depends on the depth of the soft clay. But usually, in soft clays, the if dealing with buildings, you're going to like to use driven piles. Driven steel piles usually are the best. The second would be concrete piles. But for a very large structure, you're going to need a much deeper foundation. You have to go to very large diameter board piles. So it varies. There's no one suggestion, but depends on the kind of type of structure and the soil conditions. Okay. Anyway, I'll be available to do any further discussion with anyone. Just send me an email and I could do that. Okay. Thank you very much. Thank you.